Okay, we're going to be working problem 691. It is a typical machines and frames problem. We're going to take a look at the schematic that we're given out of the book. We've sort of made an FBD rendition of that. What we have here is some sort of horizontal plate or some kind of object being held by these two clamp machines. And there's two chains with tensions P that are holding this thing up. And what we're asked to solve for are the reaction forces in the pin at C and the normal forces against the plate at B and A for each of these clamps. So to start off, we're going to create an approach in a step-by-step order of how we're going to tackle this problem. The first of which is going to be to draw an FBD of the entire structure, which we've already sort of created over here. And using that FBD, we're going to create some equilibrium equations and solve for any reaction forces that we can. Next, we're going to do a method of sections cut to divide the machine into pieces or members that we can generate more equilibrium equations to hopefully solve for the unknowns that we need to solve. Okay, so to start our first step, we have the FBD of the entire structure. So we can generate an equilibrium equation for this. We know the weight of the object is given to us by the problem. They tell us that its mass is 500 kilograms. So to convert that to newtons, so we have something to work with, we would multiply that times the acceleration due to gravity to convert this to 4,900 newtons, which is 4.9 kilonewtons, just to shrink our number down to some smaller digits to work with. Okay, so knowing that the weight is 4.9 kilonewtons, we can write a sum of the forces in the y equilibrium equation with the up direction being positive, which would be equal to 2 times p. These are p plus p minus the weight w equals to 0. Plugging in what we know, we can solve for p to be 2.45 kilonewtons. So each chain is 2.45 kilonewtons in tension. So in order to solve for the pin joint and the normal forces, we can look at the entire FBD and see that there is symmetry in the structure, meaning that everything on this side of the structure must equal to this side of the structure. So we can simplify this problem by just working with one clamp instead of the two together. So the FBD that you see here is this part of the structure alone. Okay, with this FBD, we're really generating equilibrium equations with this FBD will not really lead us to any information that we can solve for that will answer the problem. So in order to break this down, we'll have to do a section cut at the pin joint C that will divide this up into two separate members, which will expose the internal forces in this joint and allow us to generate some equilibrium equations to solve for the normal forces. So that's what we do over here. This is the larger member. We've exposed these internal forces Cy, Cx of the pin joint. We have our chain force P that we know, and the normal force A, where the object is pushing up against this piece. So to start running through our equilibrium equations, we started with the sum of the forces in the x, being the right direction being the positive direction. The only force we have in the right is Cx, which would lead us to already answer this part of the problem, being Cx equals 0 kilonewtons. Some of the forces in the y with up being positive would be equal to Cy plus the normal force plus the tension P equal to 0. And the sum of the moments, which we picked point C, since we know P and we don't know NA, we'll only have one unknown to solve for, which will allow us to solve for NA, which is one of the answers to the problem. So we'll do our moment around pin joint C. which is equal clockwise or counterclockwise, being the positive direction. So negative P times 0.15 plus the normal force A times 0.08 is equal to 0. We know P, so we plug in 2.45 for this variable, then we solve for NA. We get 4.6 kilonewtons as the answer for NA. So the only thing left is CY and MB. Well, this is where this equation can come into play. We know P, we know NA. We plug that information in here. CY plus 4.6 plus 2.45 equals 0. Solve for CY. CY equals negative 7.05 kilonewtons. So the only thing left to solve for will be MB. MB is not listed in this FBD, so we look at the other piece of the machine. Here we see MB and the pin joint internal forces that we know. So we can simply do one more equilibrium equation to solve for that force. Sum of the forces Fy being the positive direction, we equal to negative MB minus Cy equals 0. Plug in Cy, which was negative 7.05, and solve for MB to get 7.05. So our answers are in squares.